Right, wait. Assalamualaikum warahmatullahi wabarakatuh. So today we see how we want to design the FET common source design. Um, so this is the circuit. So we need to determine the value of RD, RG, RS, and the transistor that you are using here is 2N5556. So this is the requirement lah for our design specification. So we have the AB, VCC is ranged between 10 volt to 20 volt, and we have the VO max, and this is the Z in, also the Z in, and also the ZO requirement. So we download the data sheet, and this is the for the transistor 2N5556. So we have the VGS off, which is represent the VP, and IDSS. So here we have the minimum and also the maximum. Then we take the middle value. So we have the value is the average value is around 1.5 milliampere, and then we have the value of pitch of voltage around negative 2.1 volt. Okay, so this is from the value from the data sheet, and then we draw the AC equivalent circuit, and we calculate the gain, Z in, and also the ZO equation. So from here, from our gain value, gain equation, so we have the AB is around equal to GM times with the RD. So here we need to change the value of resistor RD into the so we have the term we have the term AB equation in term of the resistance to the voltage. Okay, so this is the process how you want to convert the AB equation so that it can give our final value in term of voltage. So we have the GM equation, so we replace here, and then we simplify our equation, and we have the RD equation, which is equal to VO max, the maximum output swing, divided with the ID, and we have the ID equation also here. Then all these two equation will insert in our AB equation, and then we simplify. So this is the step where you can simplify all the equation, and this is the our final equation, which is represent the where represent in term of voltage. So we have the VGS equal to 1 subtract with the 2 times VO max over VP times the pitch of voltage, and then we time with the VP. So here we set all this equation here, this part as alpha, and we have then we have the equation of VGS equal to alpha times VP, where alpha cannot exceed more than 1. So you can set any value here. So for this case, we set VGS equal to 0.25, and then we can get the value of VGS. From the VGS value, then we can check uh, where our AV is meet the specification or not. So here when we set the uh, alpha equal to 0.25, then we take we put all the value here. This one is the AV, and so the VO max is around 2.5 volt from the given specification, and we get the final value of AV is equal to 3.17. So here is the value of ID, and this is the value of the VO max. We get around 2.98, and here we set the value of we know that this one is the self bias, where current, which is in our gate region, is around 0. So we get the VG is around 0, so VGS equal to VG subtract with the VS, and we have the VS here is around 0.525 volt. So this VS is equal to the V losses, and we have the RS here. RS is equal to 0.525 volt divided with our ID, and we get the RS value around 625, and RG we set more than 1 mega ohm. So we set to the RG we need to set more than 500 kilo ohm. So we set around 10 mega ohm, which is represent our Z in. Okay, so this is the AC and also the DC load line. So we set our voltage 15 VCC, and we have the V losses at the source. Then we subtract 15 subtract between 0.535, and we get the VDS here. Then we subtract with the maximum output swing, which is we set 2.5 volt. Then we get the VDSQ here around 11.98 or near to the 12 volt. Okay, so now we draw our circuit so that we can determine the value of ID, VDS, and then we plot our AC equivalent circuit. And we plot the uh, our graph, which is AC analysis. Okay, so we open the LT spice here. Okay, we take all the resistor. Uh, 625. This one we set to 1 micro, 1 micro. Yes. C, CO, nano, one is 100K. One is our VSS 15. 2.98. So we change with find out 2 and 5 5 5 6 5 5 5 6 2 and 5 5 5 6 5 5 6 4 5 5 2 and J K J 2 and J. So we take from our model, search for 2 and 5 5 5 6 perfect spice model. Take from this one, 2 and 5 5 5 6. Okay, so we take from this model. It might be change our take from this model, basically might be change our voltage and also our current also. Never mind, we try first. Select spice derivative. Okay, and we name okay, so we put label here, VG here, yes. This one we call as a VD. This one is our voltage source. And label VE. And this one is VO. Okay. So we have voltage at the source 0.36. So our estimate is 0.5. It might be changed because our transistor take from our spice model. It might be changed. If the built-in, more accurate lah. Okay, so we S VD. So VD minus with our voltage source take around 11, 12, around 12 something. Okay, so kita ada 13.2 tolak dengan 0.7. Kita ada 13.2 tolak dengan 0.3. 12 kita target around 11 volt. Okay, 11, 12 dekat lah VDS kita. And our current ID is around 0.6 milliampere. So this one 0.8 milliampere. So slightly different. So however, so we try to simulate our AC analysis. Then we change this to 1 10 milli. Then we run to AC analysis, linear number 500, 10 gig. run again. So we set loss. Oh, okay, we need to run again here. Trace. So we in. Sorry, VO. VO divide with we in. Okay, so we change again. Copy everything. 10 max. We in 100. Okay, and make. Then we put again we put some extra around again. Okay, so we get this display this one set to the linear, so we get around 6.7. So our target is 3 point from the our calculation. Our gain is 3.17, so we double up around 6 here. This is because our we take the spice model from the our this one. Okay, so we need to consider more in our, if we have the built-in, so we have more accurate lah. Okay, so it's okay, but as long we can determine the value of we have the value of gain slightly different, but this is the step of if you want to design the self-bias FET transistor. Okay, hopefully you can follow and apply and try to redo again so that you can gain your knowledge. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.